Okay, good morning and welcome everyone to the final day of the program. The first speaker of the day is Erez Nesharim from Israel, Technion, Israel Institute of Technology. Today he will speak on bounded orbits for diagonal flows on the space of lattices. Erez.
Thank you. Thank you for the introduction. Thank you for coming. So I thought I'll start with an outline of what we talked about from the first day. So we started with the Dani correspondence for bounded orbits. Then we proved that the set of badly approximable numbers is absolutely winning using the simplex lemma or using this geometric construction. Then this is where we are roughly, because we almost finished the argument that the set of badly approximable numbers is 1/2 Cantor winning by using sort of quantitative non-divergence estimates. The next step will be bootstrapping this argument. So we'll talk about this after this. And then I will have some time to talk about the proof of the general case and tell you about some open problems. So let's go back to this BA is 1/2 Cantor winning via quantitative non-divergence. So recall. Bob chooses beta and R0. And then Alice chooses a rate in which she will avoid the cusp. So define B to the 1/2 equals beta. And that's it. And okay, and define this this flow. B to the power t, b to the minus t. So this way conjugation by A of the unipotent element will expand by beta, by 1/beta. And then assume, so for t integer, assume BT satisfies, assume that for every x in BT, A T U X is not in K epsilon. So epsilon will be roughly 1/b R0. Inside, so thank you. Then what we proved last time is that we have a measure estimate on the Lebesgue measure of this set. The set of all the points in BT such that a t plus 1 ux is not in okay. Is smaller than some constant times epsilon. It was actually a very explicit constant. It was 2 epsilon to the power times the Lebesgue measure of the ball. Okay, and the reason was that this set is composed. Well, this lattice is not in K epsilon only when there is a short vector, and those short vectors when we change x over this interval and expand by at, they look like lines, and lattices of unimodular lattices cannot have more than one vector, one short vector at a time. Well, two-dimensional unimodular lattices. So we have this picture, and we should have this picture in mind of BT. And then we have this we have some vectors, and this is okay. This is epsilon, and this is 1. And we show that that this condition implies that every vector passes 1. So we have those bunch of vectors, but all of them are well, the range where they are shorter than epsilon is disjoint, and the ratio cannot be bigger than 2 times epsilon of the whole interval. And then we are still missing a fine tuning about the fact that we want to play the epsilon Cantor game. So we want Alice to specify a collection of balls which will cover this set. And the point is that she can do that because it's exactly the step of the game that she can still do it. So if the reason that you can do that is if x is some point here, if x is here in this set, then and y, the distance between y and x is smaller than beta to the power n plus 1 R0, which is the balls that Alice can choose. Then what can we say about okay, so x is in this set. It means that there is some vector for v in Z2 such that a t plus 1 u x v is smaller than epsilon. We have that a t plus 1 of u y v is basically okay. It's if we write y equals x plus x prime with x prime that is smaller than beta to the power n plus 1 R0, then this is just a okay. This is just a conjugation of the unipotent, so it's U times beta to the power minus n plus 1 times x prime. Times this vector a t plus 1 u x b. So this is a vector of length of size epsilon, and this is a short unipotent. So the size of this is at most R0. So if you assume that R0 is small enough, let's say smaller than smaller than 1, then this is at most 2 epsilon. Right. So we can still apply the measure estimate to the larger set. So this means that by some standard covering argument, Alice can cover this dangerous set by how many balls? So okay, so Alice can cover the dangerous set. By at most the measure of the well 2 epsilon times the measure of the ball divided by the measure of well, the measure of the small balls that Alice can pick. So beta to the power t plus 1. Okay. So you see that this is roughly up to a constant at most. Which is okay. So epsilon was that's the main point somehow. Epsilon was roughly square root of beta. So that's 2 epsilon divided by beta to the power t plus 1 R0, and here we have beta to the t R0. So this cancels, and we are left with 2 times 2 divided by this 2 divided by R0 beta to the minus 1/2. There is a 2. Yes, but here should be 2 as well, right? Okay, so this is maybe somehow I'm ignoring these constants all over. So this shows that that the set is epsilon alpha Cantor winning for every alpha, which is strictly smaller than 1/2, which is actually equivalent to being alpha Cantor winning for exactly 1/2. Okay, so what I wanted to draw a picture. Just to make sure that see what's going on is that this is this idea of proof appeared in some of the talks already, in Kleinbock's talk in particular. You have this Horo cycle. You push it by AT, then it becomes large horocycle, and the time it spends in the cusp is small. And the most importantly, it's not just it's a quantitative estimate. So the fact that this is quantitative and not just saying that there is some proportion of the measure of the horocycle that stays in the cusp, but exactly there is this exact proportion that depends on epsilon. This is what allows to get winning out of a measure estimate. So maybe I just wanted to say how tight is this measure estimate. So this is a remark. Right. So what is this set? What is this x in BH dt such that a t plus 1 and ux is not okay epsilon? That's really that's exactly the union over all rationals d to the power n plus 1 and those intervals p over q plus epsilon and q to the power b n plus 1 minus epsilon to the power b n. And it's actually not so difficult to get a measure estimate of this set in a very in a very concrete way. So I mean maybe this intersects BT, right? Okay, so okay, and P is also running over the integers. So how many for each denominator? How many numerators are there? So the measure of that, the big measure of that is sum of q smaller than delta q. Q times the length, the size of the interval, plus at most like an error, multiplied by delta here is epsilon. Q and large Q is just epsilon b power n. And the size of each of them is 2 times epsilon divided by q b to the power n plus 1. So just doing the computation gives this cancelled, right? So we get epsilon times b to the power n plus 1, and this epsilon b to the power n plus 1 also cancels. So it's 2 times epsilon squared, the measure of the ball. Smaller than, plus some error. So the error is 2 epsilon divided by u divided by b to the power n plus 1. And for some reason, I have a logarithm. Yes, because that's the sum of it doesn't the q cancels here, but it doesn't cancel from this sum. So we get the summation of 1 over q. So you get something that's like a logarithm. So you see that I did this computation to show that the correct estimate somehow is actually epsilon squared. And this is also dynamically what's going on here is that we are not really looking at all the Horo cycle, which will equidistribute. So it will spend here in the cusp, it will spend just the amount of time that it spends in the cusp should be proportional to the volume of the cusp. But we are just getting a worse estimate. We are just using the fact that if it goes to the cusp, then it must also spend some time not in the cusp. Right? So we are just using a rough estimate, but it's good for it serves us well because in this estimate we don't have actually control over this error. So this estimate will be good enough for n large enough, such that b1 over bn plus 1 will be related to the size of the interval. So this kind of estimate will not help us to prove counterweighting, prove what we need. Okay. The reason I'm showing it is that if we could do epsilon squared here and have a uniform estimate with epsilon squared, then we could upgrade to absolute winning. But the truth is that we cannot. So the idea is actually goes back to Furstenberg. This is the idea of intersecting when you have some generic phenomena. You think you might want to intersect to show if this generic phenomena happens also on a fractal or on another maybe on a generic set for another dynamical system. So in the first place where it appeared in the Offenstein approximation, as far as I'm concerned, is in a paper of Barak. I don't know what I'm moving here. So I'm going to talk about this now, how to bootstrap to absolute meaning. So there was a paper of Barak Weiss about in 2000 about almost no point on the Cantor set is very well approximable. And then this somehow became a very well, a topic that many people were interested in. So there was the paper of Kleinbucklin and Weiss, and there was a paper of Badziachin, Pollington, Badziachin. There was a paper by Pollington, Dani. And even I had in my PhD, I had in my thesis there is some another instance of this phenomena where you want to study Diophantine properties of points in a fractal set. So this is the way we will bootstrap. So okay, so the idea is repeat for other measures from other measures other than Lebesgue. Okay, and here the notion that is useful is the notion of alpha regular measures. So let me define this. Mu. So let X be a metric space. Metric space. Mu a Borel measure. Is alpha regular. Let's call it alpha. Okay, alpha regular. If there exists some constants A and alpha such that and R0 such that the measure of balls of size of radius less than such that for every X in the support of mu, the measure of a ball of radius R around the support around the X is roughly the radius to the power alpha. So now exactly the same argument works for showing that so theorem BA intersection. So if mu is alpha regular, right? Or mu alpha regular. Okay, alpha is bigger than 0. Regular. BA intersection with the support of mu is alpha over 2. Alpha regular on R on the real line is alpha over 2 Cantor winning. So in particular, it's not empty. Because the set is alphas regular, so it means that if you want to cover it with balls of radius beta, then you have roughly beta to the minus alpha balls. And if you can win the alpha over 2 Cantor game, it means that you remove much less than what you have there. By a theorem from so this is the converse from a paper with Badziachin, Harap, and myself and Simons, which is still not which is still a preprint, but was written a long time ago. This implies that you're absolutely meaning that BA is absolutely. If a set intersects the support of every alphas regular measure, then it's absolutely meaning. And we sort of saw the hints to that last time, where we had this characterization of Cantor winning sets by intersection with what I call their delta diffuse sets. If you have enough, yes. Okay. Any questions? And the argument, well, I didn't write it explicitly, but it's exactly the same argument, because all we have here is when we just repeat the same argument, that the argument for this theorem. So the proof of the theorem is exactly this diagram. I mean, it's just about first of all, showing that every vector that in every one of those short vectors become large in this large interval, and the proportion of the measure that it occupies is less than epsilon to the power alpha, because it will be yes. And I'm saying that in dimension 1, it's just immediate from this description of the bed set, the dangerous set. So when we moved from a measure estimate to a covering, when we moved from an actual description of the bed set to a measure estimate, we lost some information. And now, intersecting this situation with the support of an alphas regular measure, somehow we gain back this information without working too hard. So this is the main point for 5, for the next step. So yes. So the main idea is that the measure, well, intersecting the set of badly approximable with the support of the measure is not related, is independent from the dynamical argument. So somehow nobody tells you that that you have to delve into the fractal at the same rate that you delve into the set of badly approximable numbers. The constructions are not supposed to do not have to be related to each other. So, hopefully this. So the reason I can apply is just that there is a description. There is a description of the dangerous set. Those are these intervals, and they lie in bigger intervals. So the proportion of the set where of this set and that set, for that you don't need to assume that you measure the size of balls using the Lebesgue measure. You can measure the size of the balls using this Alphonse regular measure, because maybe I should write this because maybe this is the reason that it works, is that if X is in the support of mu, then the measure of a ball around mu, around X of radius R, or of radius epsilon, divided by the measure of the ball of radius R, is epsilon up to a constant. Well, really, it is smaller than a squared epsilon over R to the alpha. Okay, so this is why you get here this alpha over squared, alpha over 2. Because in our case, R was 1 and epsilon was beta to the power of minus 1/2. The 2 is coming from the fact that we took our epsilon was not optimal. We cannot prove such as this already appeared in the Lebesgue measure estimate, right? We have a very uniform estimate. It holds for every interval. We don't need to assume anything like this here. We don't need to assume that our parameter of time is related to the denominator. But we pay by this that the measure estimate is not optimal. It's not exactly what we expect from a unipot orbit that equidistributes. But it's still good enough for counterweighting. This. So for us, we applied this. We applied this with epsilon equals beta to the minus half, beta to the half. Remember, it was 1 over b r0, which is beta to the minus half, 1 over r0. So this is where the 1 over 2 comes from. Okay, so if there are no more questions, I'll start. I will talk about 5 now. I will talk about the general case. So for the general case, we need the definition. So okay, so I want to define this this collection H. Okay, so every A and B, a matrix in M times M, and B, a matrix in N times M, such that the rank of AB is M. I can define this hypersurface of all the matrices in M times M, such that AX plus B, the determinant of AX plus B is 0. So this is a generalization of a hyperplane to the case of matrices. And I want to define this collection H. So in the case of n equals 1, for example, this is just a hyperplane. And this collection is the collection of all hypersurfaces of this form. So in the general case, we don't expect to be able to intersect every Alphonse regular measure because those can be, for example, supported on hyperplanes. So we need this definition of H decaying. So mu is H absolutely decaying. So mu is a measure on the set of matrices, and it's absolutely decaying if there is some D delta and R0 such that for every X in the support of mu, the measure of a ball around every one of those hypersurfaces of radius epsilon intersected with the ball is smaller than D times epsilon to the power, epsilon over R to the power delta, the measure of the ball. Maybe I should draw a picture. So in general, you should think of something like this. This appeared in Shreyasa talk yesterday. Shreyasi. So it just means that the measure of the ball is not exhausted by small neighborhoods of hyperplane. And now the higher dimension analog of this measure estimate that we discussed is a theorem originally due to Kleinbock-Lindenstrauss-Weiss theorem. Kleinbock-Lindenstrauss and Strauss-Weiss in 2005, but in this generality, it was probably in Kleinbock, Margulis, Wang in 2011. Or I guess I should also mention Beresnevich, Kleinbock, Margulis. So if mu is delta H absolutely decaying, and alpha is regular, alpha is regular, and it satisfies this condition that okay, G U X V is bigger than 1 for some the supremum over the ball. Or maybe I should say something. Okay, let me write this. So the measure then. So there is some ball, but I should put it somewhere in the quantifiers. So but if this ball satisfies this property and G, there is some diagonal matrix G, then the measure of the set of points in the ball such that G U X is not in K epsilon is smaller than constant and epsilon to the alpha gamma times the measure of the ball. So there are many quantifiers that I should write. But you should feel comfortable by now with this kind of estimate because it's exactly the generalization of the one-dimensional thing that we did. So what is it? So there exists some constant C for every D delta and alpha. There exists some constant C and gamma such that for every ball and for every G, here I put Beresnevich, Kleinbock, Margulis in 2013, and every G, which actually I should have written AW. So it is some diagonal matrix that expands the first M coordinates and positive and contracts the rest. Okay. So this is somehow the main ingredient to the general proof, the general case. So here's a theorem. Let me write this in small t because it's not written completely yet. So that's Veresnevich, Nesharim, Dani, and Young. That and to be safe, I'm saying that BAW is H absolute meaning. Which means that I'm allowing Alice to remove neighborhoods of hypersurfaces. So proof. I'm not going to be able to prove, but I'm going to give you at least some idea. Idea of the proof. So most of the ingredients are already here. There is just one technical question. One technical difficulty. So the idea is to take any measure, mu, alpha regular and decaying, alpha regular decaying, absolutely decaying. And now play the same game that we did in the one-dimensional case. So let Bob choose. Let Bob choose beta and R0. Define B as okay. B will be the right rate, which expands in which the most it expands, it will not be faster than beta. So in the coordinate that it expands the most. So it's beta to the power W1 minus Wm border m plus n. And now here is the main, here's the key claim, claim. So for every parameters T, T1, T2, T3, if so there is going to be some condition here, and the conclusion will be that the measure of the set of matrices in BT. So we're assuming that the game goes on, and this is the ball that was picked on the T stage. Now I'm looking at this diagonal element 81 at time 81 applied to this unipotent, and I'm asking for it to be not in K epsilon. But epsilon is going to be very explicit, but doesn't matter. For now, it doesn't. For here, it doesn't matter because we'll have this estimate will be correct for every epsilon. The epsilon alpha. The measure of the ball. But the condition is exactly the same condition that we, in the spirit of what we had before, right? We'll have to verify that all vectors. Okay, maybe. I didn't say this, but here V. It's important that V will be a wedge product. So V. Okay, this is very important. for every V, which is in the outer product of Zn plus n. Okay, and the idea is that for higher dimensional lattices, there could be situations where there are more than one short vectors. But then if there are two short vectors, then they become a short subspace. So this gives you a way to control the situation, even in the higher dimensional case. Okay, so we'll have to the condition. What? So the condition that we'll have to verify here is that there will be no wedge product. I guess maybe it's not the completely correct to write here this way. So this is, I really mean a subspace. So I really mean what's called decomposable. So decomposable. So it is an actual wedge product of some k vectors. So it's an actual rational subspace. So we'll have to verify that there are no wedge products that remain small for a long time. But if there is one, then there will be a condition, and the condition will be that some lattice was high in the cusp. But unfortunately, this lattice is not one of those. Is not anymore one of these lattices. So it's a lattice that comes from a different one-parameter flow. So let me define those two. Actually, there are two other one-parameter flows. So I'll define them here. There is this D, which is given by D, which is given by beta to the power. Okay, this is quite involved. So there are those weights that are that have this that satisfy this inequalities, right? And there is zero somewhere here. So I'm going to define this parameter. So there could be some weights that are equal in the beginning, and some weights that are equal in the end. I'm going to define this parameter by M0 and N0. And then there are two one-parameter flows, beta to the power M plus N minus M0 divided by M plus N. And at some point, this is M times. And 0 times. And the rest is to make this diagonal matrix determinant 1. So it's M plus N, and so on. So this is one parameter flow, one of them, and the other one is the tilde, which is beta to the power N0 over M plus N, and beta to the power M plus N minus N0 over M plus N. So basically, those are matrices that, this is the matrix that shrinks those components that were expanded the most. And this is the matrix that shrinks wait, I need a minus somewhere. That there is t. I mean, you can take to the power t if you want. You can take those to the power t, or just add here t. Okay. Now I will very soon. I hope I have time. Yes. So I'll very soon draw a picture in 2 dimensions, so it will be more clear, hopefully. So what are the conditions? There are 2 conditions, if 1 and 2. So 1 and 2 are, if you go back, so either you go back with the d tilde, t2 seconds, or you go back with t with the d, t3 seconds. So xt is the center of the ball of bt, and then this is not in the cusp, but not in the cusp in a very quantitative way. So not in k beta to the power n0 over n plus n, t2, and here maybe up to a constant, and here it's k beta to the power, the power is more complicated, so beta to the power, let me write here tau. And I should write tau somewhere. Is this okay here? Nobody tried this before, but nobody shouts. So tau is 1 over n plus n minus 1, the maximum between minus t plus t1 minus t2 minus t3 n plus n minus n0 times n0 divided by n plus n, and n0 divided by n plus n and t3. So if you want this to be positive, and you want this to be positive because we are interested in the cases where this is a meaningful condition. So tau should be positive. It means that T1 should compensate for T, the size of the ball, for T2, T3, which are the amount of time that you go back with the other flows. And somehow you want, in order for this to be kind of optimal, you want this to be comparable to this. So you want these differences to be comparable to T3. Okay, let me draw a picture in 2 dimensions. So this is a picture I like to draw. This is okay. This is a picture of the Lie algebra of A. the diagonal subgroup, and this is the direction. Let's say this is the direction. This is 1, 1, 0, minus 1, and this is 0, 1, minus 1. So these are this is the area where our flows live. This is where, right? So this is the matrix. This is the logarithm of the matrix b to the t 1 b to the minus t. This is the direction of the matrix b to the t and 1 b to the t b to the minus t. So these are the extreme weights where they give all the way to one coordinate. And in between, there are those weights that we're interested in. Well, we're interested in these as well. And somewhere here, there is our omega w. Okay? And we are interested in studying the bounded orbits along w. And in order to do that, we need to consider also two other flows. So in the case m equals, so this is the case m equals 2 and n equals 1. So d is beta to the power correct me if I'm wrong. So beta to the power 2/3 beta minus third beta minus third. And d tilde is beta to the third, beta to the third, beta to the minus 2/3. So if I got it right, those are the two other flows. And what I'm saying is that in order to study, for example, let's say I'm here in time t1, I must know something about okay, things that happen along things that happened here. So I must know that these two flows, those two composition of flows, right? D tilde times A and D times A, they were not high in the cusp. And this is how I get my measure estimate. So okay, so from here to get from this measure estimate to get a winning set is really just induction. So it's a complicated induction, but it's induction. So you need to prove a similar estimate to those matrices as well. So it's not enough just to work here. In order to be able to show that this remains in a compact set, you have some conditions here. Okay, and you will have to deal with all of these conditions, but somehow this is going to be the basis of the induction. These areas. So you will really only need to have to deal with the finitely many conditions for every point that you want to deal with. Okay, I know this cannot be a clear explanation, but maybe hopefully you. It's a growing number, yes. If you are very far, then Yes. The strategy in the game is actually going in the other direction. So let's say you were somewhere here, and you can remove all those bad things that can happen in the future along these two lines. And then this means that when you get here, you will be able to apply the measure estimate because you already took care of lattices that were in these regions. I think I shouldn't try to prove this claim right now. But instead of that, I'm going, maybe I should. I want to say something about the curve case, about this. I'm just wondering if it will be meaningful if I didn't show you that proof. Okay, let's try. Okay, so the curve case, unless there are questions about this. Okay, let me say something about the curve case. So the curve case is basically the same, very similar up to two things. So first of all, we need some other some more precise statement here, which will involve not only, so this statement involves really one unipotent applications of diagonal matrices to unipotent orbits. So really it's a unipotent orbit. So we'll need some other measure estimate for what happens when you plug in here a curve. But this is well known by now in this quantitative non-divergence proved by Margulis, and so I'm going to assume that we know this. And the only other ingredient is a trick that allows you somehow to rotate the curve in the direction of the most expanding direction of the flow. So this is just a trick that I learned from Lei Yang. So remember that we have this Dani correspondence about, so it's related to, so let's say F is a curve in out to the end. It will be more convenient to just work with the m equals 1. And we want to discuss this badly bounded orbit. So we have this orbit of diagonal orbit of UFX call it this way. So is bounded. I mean, fx is BA, BAW is in BAW, if and only if this orbit is bounded for positive t. But it will not matter much if I add something that shrink along the flow. So the trick is to instead, and this is true if and only if A, T, U, really I want to say W, F prime, X, U, Fx, where, so if and only if this orbit is bounded for positive t for W, y equals this matrix. So y, y1, y2, yn, and one's on the diagonal. And the reason this is useful is because right now I'll just show you what happens to nearby points. Okay, so how does if x equals x0 plus x prime, then how does W f prime x U fx looks like? I'm just going to use the Taylor expansion. So F double prime at F prime double prime 0. That's the first order approximation at 0. Times U. Okay, x prime f tag 0, U x 0, and now f f of x. So now what's in order to show what is the difference between that and W times U of x0, I just need to change the order of W and U. Okay, so you can think of y1 as being 1. So this is a simplifying assumption, which you can do, right? Because your curve, you can always assume that the curve is not flat. I mean, we are assuming that, and it means that you can assume that locally you can parameterize the curve by the first coordinate. This is, okay. I did this computation, but it should be so it should be W of x prime s double prime x0 times u of x comma zeros x prime. Okay, so this is the point that we wanted to show how close we are, and this is what happens to, and this is negligible. So we can forget about this. Let's say, I mean, it's not true that it's negligible. It's negligible in some regions, because what I'm going to do next is I'm going to apply 80 to that. So somewhat, I mean, it needs to be done very carefully, more carefully than what I did. But using this trick, we get a unipotent exactly in the direction that's expanding the most. So now, okay, now basically I'm done with what I wanted to say about the curve case. Okay, this is it's a bit difficult to explain because I didn't explain the proof of that case, but it's very similar now to the one-dimensional case actually. So imagine that you have a vector or a wedge product that remains small for a long time for the interval bt. Then so after conjugating, it means that it stays for a long time, for really a long time, because this is where the shift is happening. So you conjugate with the highest rate, with the highest rate expansion. So then you will be able to get something meaningful out of this. Again, not what you would like to, right? You would not be able to apply the same flow to go back, but there will be some other flow that you will be able to apply. Okay, I wanted to mention at least one open problem or two. The condition is basically that it satisfies the conclusion of this measure estimate. So you will be safe if you will assume that it is analytic and non-degenerate. It's not contained in a hyper. Not contained in one of those. Yeah, if you are we are working in the n equals 1 case, so not contained in a hyperplane. Yes. If you plug here f, I guess one should be more careful because there will be some other constant appearing here, maybe. Okay, so open problems. Apart from Ango and Kleinbock, which means to generalize this now to every Lie group, I think a very interesting and challenging one will be to find conditions on a hyperplane or a hypersurface, one of those hypersurfaces such that BA intersection with the H is well, H absolutely meaning. So this is not known. It's not completely known even in the case of lines, even for lines in the plane. So it's not completely solved even for lines in the plane. And another very interesting and I think challenging problem is okay. You can talk about the inhomogeneous approximation, but a more general situation is when you have a sequence of matrices that is lacunary, so W lacunary. So you have a weight. So it means that you have a way to measure size of vectors in Rm and Rn. This gives you a way to measure the operator norm of a matrix. And then you can define what it means to be lacunary, that the operator norms. So these operator norms are bounded away from 1. And you asked a question about the set of points that you do not come close to when you apply those matrices to rationals. So maybe. Yes. No, XKs are general matrices. So it's a generalization of what happens when you multiply by 2 modulo 1, right? You look on just any vector V, I guess, in Rn, and you want to look at x times V and see how far it is from integers. Okay, info over k and over t, an integer vector. So here it's n. You measure the distances with the weighted norm. So it's W plus. And you want this to be non-negative. So prove that this is how this set is hyperplanar. Okay, this is known for the equal weights case, but okay. Thank you.
Thank you for the series of lectures. Are there any questions or comments?
You gave a theorem with a small t, but in the case either n equals 1 or m equals 1, I forget, this is a known result, right?
Yes.
This is, so which, what are the difficult parts of extending this to general n and m? I mean, in your scheme, like what could be simplified if we assume n equals 1?
Okay, so in the case of vectors, you can get away with just one other diagonal flow, because somehow you can just instead of one of those diagonal flows, you can apply the original flow, and then it shouldn't be a major issue, but makes the induction somehow more complicated to see.
Any other questions?
There is also this issue with removing this annoying relation to those hypersurfaces instead of absolutely hyperplanes, because I mean, this can be avoided by considering the general case of embedding. So hopefully we'll prove in the end something stronger about so the maps will not be curves, there will be general manifolds, and then using these if we could prove this the same on manifolds, then this will already imply that we can get rid of this hyperplane, these hypersurfaces, these restrictions. Could be that there are other ways to get rid of that.
Okay, if there are no other questions, let's thank the speaker once again.